Okay. Let's bring up the notebook. Okay, there it is. Okay, so as I was saying, I want to just go over the couple of slides of explanation, and then we'll look at example one. Example two is not something we'll have time to get into today, and so I'm excluding it from the final. Okay. All right. So we talked about complex power. Complex power is basically the total power that is being supplied in a circuit in response to an AC voltage or AC current, and um, it comprises of the real power of the resistive components as well as the reactive power that is associated with the reactive components, basically the inductors and the capacitors. Okay, inductors and capacitors have reactance, and the power associated with this reactance is known as reactive power, noted by the letter Q, units VAR, volt ampere reactive. Impedance for a inductor, reactance and impedance for an inductor is always positive. Reactance and impedance for a capacitor is always negative, right? That comes from the fact that the voltage leads the current in an inductor, and the voltage lags the current for a capacitor. Okay, so impedance, of course, would be theta V minus theta I, the phase difference of the voltage and the current. And so for an inductor, it will always be positive. For a capacitor, it's always negative. So the reactive power associated with the inductor and the capacitor is always positive and negative, respectively. QL is always positive. QC is always negative. Yes. Mm. Yes. Yeah, it's associated with the reactance. Yeah. Now, in real life, of course, the utility company has to send the currents and the voltages associated with the reactive power also. So it's not separate. It's not separate. Okay, it's the exact same thing. Meaning you're sending, let's say you're sending 100 VA, 100 volt ampere total complex power. Some portion of it will be used for the reactance. Some portion of it would be used for the resistive work. So it's not separate. Mathematically, we represent it separately because some power is used in the reactance, some would be used in the resistive portion. Yes, that's the real. Yeah. Yes. Yes. Yeah. Not compensate, but it's all together is one number. All put together is one number. So in real life, it's the voltage is still being sent. Voltage, of course, will remain constant, but the currents associated with both the real power and the reactive power be now much higher. And current is basically why the high amount of current is why we want to reduce the reactive power requirements. So the other equations that we look at for the reactive power, they follow the same form that we already saw in chapter 1. Okay, power can be given by I squared times R or V squared over R from chapter 1. Okay, it's still the exact same form. For an AC circuit, if you have R, L, and C, you would use the RMS values for the voltage and current of that particular component, and the equation would still have the exact same form. So for a resistor in an AC circuit, the power would be given by the RMS value of the current or the RMS value of the voltage. So I square or IRMS squared times R and VRMS squared over R. When it comes to the inductor and capacitor, same form, same structure, the same equation, except inductors and capacitors do not have resistance, they have reactance. And so the same form of the equation would become V RMS square over XL or over XC. If it's current, then it's I RMS square times XL or times XC. These equations, of course, apply to both inductor and capacitor. Okay. One thing I'd like to point out, there are multiple equations that apply equally to all components. Okay, as engineers, it's up to you on which approach and which equations you'd like to use. Just take the example of a resistor, for instance. If we talk of the resistor, we can find power in 3 different ways, right? Power is the product of the voltage and current, V times I. So if you think back to chapter 1, if we wish to find the power for a resistor, we would simply find the voltage for that resistor, we would find the current for that resistor, and take the product. VR times IR would give us, right? P is equal to V times I would give us the power for that resistor. If we wish to skip that step, we would simply find the voltage or the current, just one quantity. We don't have to find the voltage or the current. We do not have to find both. We simply take the voltage and do V squared over R, or we take the current I and do I squared times R. Does that make sense to everyone? Right? Think back to chapter 1, which is like the first week of classes, 8-9 weeks ago. So when we try to find AC power, we still follow the same rules. Everything still applies, whether it's resistor, inductor, or capacitor. For an AC circuit, the same rules still apply. You can find the power, whether it's P or whether it's Q, by finding the voltage and the current for that particular component. You can find the voltage and current for that component and apply equations. There are separate equations for that because it's complex quantities. It's not as simple as simply just multiplying the magnitudes. We have to take the phase angles into account. Or if you want to find it directly from the reactance and the resistance, we use the equations I squared times X and V squared over X. But in all cases, we use the RMS values for the voltages and the currents. Okay. So that's where these equations come from. All right. Now, total complex power, S, is the sum of the real power P and the reactive power Q. Simply P plus Q. But mathematically, we use complex numbers to make the math easier. So it's P plus JQ. We saw that in the previous slide, right? S, total complex power, is P plus JQ. Okay. In real life, both are real. This is just mathematical representation. Q is represented mathematically with the imaginary number. But in real life, it is P plus Q. Okay. So since complex power S is a complex quantity, it has magnitude as well as phase. So S can be described as magnitude of S with a phase angle theta. This theta is also the power angle, which we looked at in this slide right here. Okay. I didn't list all of the equations on one slide because it just gets too confusing. So I might have to skip back and forth because they're all related together. So this theta is the power angle as the difference between the phase angles of the voltage and the current, theta V minus theta I. Okay. Those angles we'd get from the phasor form or phasor representation of the source, whether it's the voltage or a current. So theta V minus theta I. And because it's a complex quantity with real power and reactive power, we get a power triangle, right? Power triangle. So from this power triangle, we can have two more equations. Real power P can be described as the magnitude of S, cosine of theta, and magnitude of S sine theta. Trigonometric identities. Yes. Phasor form requires magnitude and phase angle. Magnitude is the peak value. To get the RMS, we divide by √2. Make sense? And we look at that in the example. But as I was saying, so when you join the hypotenuse, when you join the two sides of the triangle with the hypotenuse, that gives you the magnitude of S. The magnitude of S is the product of the voltage and current, the RMS values of the voltage and current. So it's VRMS times IRMS, and it's trigonometric identity. So you can describe P, real power P, as magnitude of S, which is the hypotenuse, times cosine of theta, cos theta. Hence, we get the equation VRMS IRMS times cos theta. And the same thing for Q, reactive power Q. Okay, so we can use these equations to find power for every single component, or we can use these equations also to find the power for every component. Okay, there are multiple equations that you can use, and we will see in example 1 where I have 3 different approaches to find the total complex power S. Okay. Okay. Magnitude of S is also known as apparent power. Okay, apparent power. This is important for technicians and engineers, because people, when they actually work on these electrical lines, this RMS value is the one that they will actually encounter, right? When they do measurements, when they working on electrification of the lines. Okay, and then moving to the top of the slide, we come to a new term known as the power factor. Power factor simply describes whether the load is inductive or capacitive. Okay, it describes whether the load is inductive or capacitive, and it is describing the phase relationship of the current with reference to the voltage. If current I leads voltage, then we say power factor is leading. If current I lags the voltage, then we say power factor is lagging. Okay. This comes from the fact that for an inductor, the voltage always leads, and for a capacitor, the current always leads. If you need help, we can turn to Eli Manning and use this mnemonic, Eli the Iceman. It's not really named after Eli Manning. L stands for inductor, C stands for capacitor, E stands for electromotive force or voltage. I, of course, is current. So for an inductor, the voltage comes before the current. And so voltage leads the current. Or in other words, you can write I lags V. For a capacitor, current leads voltage, or you can write actually V lags current. For power factor, we are just interested in the description of the current with reference to the voltage. Meaning, If current leads, then the power factor is leading. If current lags, then the power factor is lagging. Most industrial environments, actually almost all industrial environments that have electric machines running as loads, will all be inductive. So power factor for an industrial client or an industrial customer is always lagging. Okay. So power factor simply describes the relationship of the current with respect to the voltage. So power factor in an industrial environment will always be lagging. Mathematically, power factor is given by the cosine of the power angle. Okay, cosine of the power angle. Power angle is the phase difference between the voltage and current. Theta V minus theta I. It's a cosine of that angle gives you the power factor. And it is expressed as a percentage. It's always expressed as a percentage. So if you take a resistor, for instance, the power for a resistor will simply be the product of the voltage and current, or V square R, V square RMS divided by R, or I square RMS times R. But the phase difference for the voltage and current of a resistor is equal to 0. So for a resistor, power factor is cos of 0, which is 1, described as 100%. Described as 100%. With an inductor and a capacitor, it's different. With an inductive load, if you don't balance it out with the capacitor, power factor could be anywhere between 0 and 90. And if it's less than a certain number, the utility company will not supply electricity to that consumer or that client. Okay. So as an example, let's say PG&E sets a limit of 85% for power factor, which would mean 0.85. If an industrial client drops below 85% as their power factor, they would say, PG&E would say, hey, you need to bring your power factor above 85%. Otherwise, we will not supply electricity to you. Okay. So again, the power angle needs to be at a certain level. Remember, the power angle is larger as the reactive power requirement goes high, right? We need to balance it out by applying a capacitive reactive power in the negative or the opposite direction. QL is positive, right? QL is positive going up. You place a bank of capacitors in front of the inductor, and then it brings it down. The goal is to bring it down to as close to 0 as possible. Because if it's 0, power factor is 100%. Let's take a 10-second pause. Think over that. Let me know if you have any questions. Any questions? Yes. I've pretty much never seen a circuit that does not have any resistor. But yes, technically your answer is, your question is valid. If there is no resistor in the circuit, there will not be any real power. But real life inductors and capacitors will have resistance. Even high quality inductors have 5 or 6 ohm resistance. So there's always some resistance present in real life. Resistance are a way to actually control the currents flowing through the circuit. So a real life circuit would not ever exclude a resistor. Let's see. Okay, any questions about this slide? Power factor, leading, lagging. All right, let's take a look at example 1. So we are given a RLC circuit resistor, inductor, capacitor, and we are asked to find power for every component. So this is a 2-for-1 problem. Okay, this problem, I will take it from the very top, and we'll do an analysis to determine the voltage and current to determine the voltage and current for every component, and then we'll find the power for every component. Yes. Similar, yes. Absolutely. Yep. So first half of the solution would be kind of an example for chapter 5, right? AC analysis. And then once we have the voltage and current values, we will go and find the power. If you find me sluggish, it's because I only had 4 hours of sleep last night. I'm not like sick or anything. Okay, so we have RLC in the circuit. All the values are given to us. As always, I always tell, as engineers, when you look at a problem, look at the entire problem statement and look at all the information that is presented and extract as much information as you can from that problem statement. Okay, and that's especially true in electrical engineering because you have information that is included in the circuit diagrams. So in this case, we are given the values of the inductor, resistor, and capacitor. We are also given the value of the voltage source, Vs of t. Okay, Vs of t. So chapter 5, we want to find the voltage and or current for every single component, right? We want to find power. So the first step is to find the voltage and current for every single component. Now, the solution is very long. The annotations and the solutions are already available to you in the class notebook. So I suggest instead of taking notes, you might want to like write down the comments and the steps that I explained here. Okay, so the first step is to, of course, draw the equivalent impedance diagram. Okay, impedance diagram, where we represent every single component by its impedance and then the sources by its phasors. Okay, that's, if you think back to chapter 5, that was always the first step for every single circuit problem. And that converts inductor into ZL, capacitor into ZC, voltage source V of t into a phasor Vs, and of course resistor remains the same. Okay, resistor of course remains the same. And that is the equivalent impedance diagram. I note the current flowing through the resistor and the capacitor, IR and IC. Again, think back to chapters 1 and 2. Okay, this is no different. Only the math is different, but the analysis technique is still the same. Okay, the source is supplying power, so the current goes from negative to positive. So again, this explanation is helpful for you because it's kind of like a recap of chapters 1 and 2. We are not given anything else except the information here. We are given the supply voltage terminals. Current for a source goes from minus to plus, so it goes in the upwards direction. There's nowhere else to go except make a right turn and flow through the inductor. So I can write that IL is equal to the source current, and I'm going to label that as I. So IL, of course, is equal to I. When it hits the top node, some of it comes down here, some of it goes through the capacitor. Actually, there should not be a turn there. This should be like this. Okay, it splits in two. So IL is the same as the total current I being supplied by the source, then is split between the parallel combination of the resistor and the capacitor. So IR and IC. If you apply KCL at the top, you have IL equals IR plus IC. I can combine the resistor and the impedance of the capacitor ZC because they are in parallel, right? You can combine impedances the same way you combine resistors. So I will label that as ZRC. ZRC is the parallel combination of R and C. When you have two components, it is simply the product of the two divided by the sum of the two. And you'll see this just down the page, right? So it'll be R times ZC divided by R plus ZC. That would give you ZRC. Then we have ZL in series with ZRC. So ZEQ, my total equivalent impedance as seen by the source, is the sum of ZL and ZRC. We're not doing anything different from chapters 1 and 2. Okay, everything is still the same. This is the first resistive circuit analysis technique that you learned in chapter 2. Series parallel equivalent analysis, where you take a network or circuit containing a large number of resistors and you compress them down to one single equivalent resistance. And so that's what we're doing here. You take three impedances and you find ZEQ. You guys with me so far? Right? So then that is still in terms of the variables. Now let's find the values. Let's take a look at the source voltage first. Whether it's a voltage or current does not matter, right? Your analysis technique depends on chapters 1 and 2. This is given to us in the sine format. If you wish to describe this as a phasor, we need to convert the sine into cosine. So sine x is cos of x minus 90. And so we subtract 90 degrees from the expression. I can write Vs of t is 10 cos of 1000 t minus 90 degrees. Phase angle for the voltage is 0 in sine format. Cosine would be minus 90. This is then equated with the standard expression, which is V of t is Vm cos of omega t plus or minus theta. So 1000 is omega, minus 90 is theta, and this is Vm, the magnitude of the voltage. Okay, so Vm, omega, and theta. Anytime you're doing chapter 5 AC analysis problems, equate it to the standard solution, standard equation, and obtain those three quantities right at the top. When you begin your solution, you want to extract those three pieces of information. Vm, the magnitude, omega, and then theta. Okay. So again, magnitude is the peak value. When we go to find the power, which is way down on this page, we need the RMS values. So we'll take the magnitude 10 divided by root 2. Okay. Again, that will come in a few steps, not just yet. Okay, so we need the omega value from the source because we want to find the impedance for the capacitor and the inductor. Impedance for the capacitor and inductor is j omega L or 1 over j omega C, not or, and 1 over j omega C. Impedance for an inductor is JXL. X, if you remember from chapter 5, is the reactance. And ZC, of course, is 1 over JXC. XL, ZL, and QL are all positive. Mathematical representation. Okay, not in real life. Power in real life is not positive or negative. Mathematical representation. And for a capacitor, XC, ZC, and QC are all negative. You might want to write that down somewhere, at least so that you remember to put it on your equation sheets. Okay, this is positive, this is negative. So ZL, j omega L gives me a value of J100 in rectangular coordinates. ZC is minus J100. Because I do not have a programmable calculator, I always find all answers for all quantities in both polar coordinates as well as rectangular coordinates. Okay, and so I perform an extra step of converting it into the polar coordinates, which of course it's also direct. The equation is omega L with an angle of plus 90, or 1 over omega C with an angle of minus 90. Again, you can refer to your equations for chapter 5. You can find it directly from there. Okay, so once I have both the rectangular and polar coordinates, I'm ready to proceed with the reduction of the circuit. ZRC is the parallel combination of R and C, or R and ZC. And so the mathematical operations here, simply plug in the values. Now I'm multiplying the top, so both are in polar coordinates, and then the rectangular coordinates in the bottom, I need to perform a division, so I'm going to change that into polar coordinates. If you have a programmable calculator, you can program this equation. You can program this equation directly in there and go directly to this final answer. Either one of those formats. Okay. That is, if you have a programmable calculator and you are confident in your skills. Because if you make a tiny error, changing a plus or a minus, or forget to input the imaginary component or the angle, your answer would be incorrect. Hence, the rest of the solution would also be incorrect. So practice as much as you can and be confident in your abilities. All right. So where was I? Oh, here. So again, R times ZC divided by R plus ZC. And I find the ZRC value as 50 minus J50 ohms. J50 minus J50 ohms. The reason I want it in rectangular coordinates is because the next step, I'm going to perform an addition or a summation. ZEQ is ZL plus ZRC. So ZEQ has a value of 50 plus J50 ohms, or in polar coordinates, it's a magnitude of 70.71 with a phase angle of 45. Phase angle of 45. And that's how I found my ZEQ. Yes. Because I'm performing an addition, yes. It is possible to do it. We'd have to use the trigonometric identities to actually do that math. It would just take longer. We actually, so that's how, before the invention of the scientific or the engineering calculators, people used to do everything manually, and that's how they did it. It just takes longer. Yes. Sure. Yeah. The impedance triangle for ZEQ. Okay. So ZEQ, let's take a look at just first the resistor, right? Resistor is given as 100 ohms. So if you put that in polar form, it is 100 with a phase angle of 0 degrees. If you put it in rectangular coordinates or rectangular form, it is 100 plus J0. Okay, so you can perform both multiplication, or you can perform all 4 operations on the resistor with just that 100 number. Okay, so that's the first step. So a resistor would simply be an arrow on the x-axis, right? Real axis. ZL, impedance of the inductor, we have, what's the magnitude? 100. That would be pointing up, the length of 100. So if this was my x-axis and this was the y-axis, this would be ZL. And then ZC, of course, is pointing straight down. Now, how many of you have done the lab? 251? Anyone? Just 2 or 3 of you? That's it? Almost all of you, right? If you remember lab number 6 phasor diagrams. It was a series circuit, right? It was a series circuit. So every component shared the same current. So you were able to plot everything on that same phasor diagram. All the voltages for the resistor, the capacitor, inductor were all in the same phasor diagram. Here, the capacitor and the inductor do not share the same current. So the phase difference between the capacitor and inductor will not necessarily be 180 degrees out of phase. The voltage and current for a capacitor will be 90 degrees out of phase, which we see here. We have 45, let's see, where ZC. ZC is minus 90, right? And the inductor is plus 90. But if you plot later on down the solution, if you look at the values for the angles of the capacitor current and the inductor current and the capacitor voltage and the inductor voltage, they will not be exactly 180 degrees because they do not share the same current. They are not in a series circuit. Okay, so I want to point this out because I remember similar questions being asked in previous quarters. It's like, you know, in one time in the lab, it was 180 degrees out of phase. You also mentioned in class it was 180 out of phase. Why is it not 180 out of phase? That's the reason why, because it's not in series. It's not this. It's not sharing the same current, or it's not sharing the same voltage, right? The voltage and the current for capacitor and inductor are different. Okay, so if we plot this, we would get the real component would be 50, and then the imaginary component is J50. So, and again, this is not to scale. So this is the real axis. This is the imaginary axis. Remember, the rectangular coordinates are the projection of that vector on the real and imaginary axis. When you take that projection and you create that triangle, that would give you the polar coordinates. So the real component for ZEQ is 50 lying on the real axis. Imaginary axis would be here. And so let's point it right here. Obviously, this is not to scale because it's 50 plus J50. They should be the same length. And that's the intersection point. So this would be the magnitude of ZEQ. And this would be the phase angle, which of course would be 45 because real component is also 50, imaginary component is also 50. So it bisects, the vector bisects the two lines exactly in the middle, half, 45. And we see that right here. And so this is the J50 portion. It's 50 plus J50, that gives you the impedance triangle. Again, it's a vector, it's a complex quantity, right? So the projection of that vector on the real and x-axis gives you the rectangular coordinates. And then the triangle, the hypotenuse of the triangle and the angle gives you the polar coordinates. Anyway, I'm gonna move along because we only have like 10 minutes remaining. So we found ZEQ. From this point, we can find everything else, right? Once you find REQ, you can apply voltage division, you can apply Ohm's law, you can apply current division, you can find the voltage and the current for all of the components using any combination of the equations that we have learned, right? So here I would apply Ohm's law and find total current I that's being supplied by the source. Simply be Vs over ZEQ. I has a value of 0.1414 with an angle of minus 135. Angle of minus 135. Keep this number in mind. 0.1414 is the magnitude of the current IM. It's the peak value. To find IRMS, I'd have to divide this by √2. IM by √2 gives me IRMS, similar to voltage RMS. Once I have I, which is the total current being supplied by the source, it is going through the inductor. I can apply Ohm's law and find the voltage across that inductor. VL would simply be I times ZL. So let's see. Let me write it here. VL is I times ZL. So practice this, right? Then that same current I is being split between the resistor and the capacitor. So total current I is being applied to ZRC. I can apply Ohm's law again and find VRC, which is the voltage across the resistor and the capacitor. So I find the voltage across the resistor and the capacitor. VRC is I times ZRC. What equation have I up? What technique do you see here? Voltage division. It's voltage division. But you can also find VRC as I times ZRC. So again, practice and you should obtain the exact same answer as here. Okay, yes. Just I. Phasors. We are still talking in terms of phasors. RMS doesn't come into the picture until we get to power. Okay. All right. So then we have that. And then we apply Ohm's law one more time. And we find IR and we find IC. Okay. IR and IC. The reason I'm finding all of these values is to show you multiple approaches. You do not have to do that. You pick and choose which approach you wish to take. Make sense? You do not have to find the voltage and current for every component. This is here just to show you that you can take multiple approaches and still arrive at the same answer, the same destination. Okay. So here on the left, I've used the expressions for power P and Q using the voltage. On the right, P and Q using the current I. Two approaches, either use voltage, either use current. You get the same answer for both. Practice this. Practice this. And then you can see 0.5 watts, 0.5 watts, minus 0.5 VAR, minus 0.5 VAR. You do this calculation, you should still arrive at 1 VAR, which is what I have on the right. Okay. So again, on the left, I used voltage for the components. On the right, I used current for the components. Two different approaches with the exact same answer. You can use V square over R or I square times R. Same answers, no difference. And here is where I use the RMS values for the voltage and the current. Okay, RMS values. XL and XC you get from ZL and ZC. It's simply the magnitude. Okay, that's the reactance without the angle, without the sign. Is that clear to everyone? Any questions? This would still be 1 VAR. So I found P, I found my total Q in the circuit. QC will have a negative sign, so it's minus 0.5 VAR. Total Q is 1, minus 0.5. So 0.5 VAR. When I add everything up, I can find the total power for the source as S is equal to P plus JQ. P is 0.5, or basically if you have multiple resistors in the circuit, you add up all of those resistors together, and that's the total real power. So PR1 plus PR2 plus so on and so forth. Here we have a single resistor, so it's just P plus JQ. Q is 1 minus 0.5. The resulting answer is 0.5 plus J.5. That's it. We found power for every single component in the circuit. Okay, found power for every single component. When it says every component, the source is also a component in the circuit. So you have to find the power for the source also. Okay, so understand that from the problem statement. The other two approaches to finding total complex power are listed below. You could use the expression S is equal to P plus JQ. You can try to find, not try, you can find the power from the total current I that was being supplied by the source and the total voltage being supplied by the source. So you have V and you have I. You have a power triangle for the source, and you can use the expression magnitude of S times cos of theta and magnitude of S times sine theta to find P and Q. Yes. Mm-hmm. Yes. Yes. If you wish to find the power angle, yes. But in this case, the phase angle is already known to us. The voltage for that comes from the phasor, right? That comes from the time varying expression V of t, and then the phasor has the phase angle, which was minus 90 at the beginning of the problem. And then for the current, it was minus 135. So we already had these values. But yeah. Mm-hmm. Yes, because we found the current I. Where is it? Here. Minus 135. Yes, we had to calculate that. Good question. Come on, what happened? Okay. All right. So as I was saying, power angle theta is the difference between voltage and current power angles. And so theta V minus theta I. Then I simply apply these equations and you get the same answer, 0.5 watts and 0.5 VAR. So if the question was just find the total power being supplied by the source, then you could simply use this because this gives you the answer in a few steps rather than trying to find the power for every single component and then adding everything up. You can simply use these equations. There is also another way, the third way to find power, which is listed below, which is even easier. That's a one-step answer, which is to use product of the voltage and current. Real power P is VI. Remember, I said it at the beginning, VI. For complex power, that equation still holds true, but mathematically, we have to take the angles into account. So it comes out to be half VI asterisk. Do you call it asterisk or do you call it star? Star is undoubtedly easier to pronounce. But I star or I asterisk notes the complex conjugate, or basically the star or the asterisk notation is saying that it is the complex conjugate of that quantity. Okay, so I star is basically the complex conjugate of the current I. It simply flips on the other side of the axis. And so a phase angle, a positive phase angle becomes a negative phase angle, and a negative phase angle becomes a positive phase angle. You're simply flipping on the x-axis. Okay, that's what I've listed here. A plus JB becomes A minus JB and vice versa. And R with a phase angle of theta is R with a phase angle of minus theta. So you can simply use this equation and find your answer in one single step. That's it. You find the total current being supplied by the source. You apply this equation and you find the total power being supplied by that source. So it depends on the question. Okay, depends on the question. You can find power for every single component, add it all up. That would be the total power being supplied by the source. That's the first step, or the first approach we took. Second approach was using the power triangle relationships. And then this third approach is, of course, just applying the equation directly. And you'd still find the exact same answer, 0.5 plus J 0.5. We're out of time. If you need to leave, you can go ahead. I'm just going to talk for a couple more minutes about the power triangle. So you plot this, you would have 0.5 on the x-axis. Oh, one announcement is basically that we'll end the quarter here today. Okay. On Friday, I'm thinking about just having kind of like an open office hours, either in person or on Zoom or both at the same time. I haven't yet decided. In the previous section, I did say we'll just have open office hours, but I'll let everyone know. But this is the end of the quarter. Example 2 will not be on the final. Okay. Go through example 2. It'll help and aid your understanding of this topic itself, but example 2 will not be on the final. So this would be PR, which would be 0.5 on the real axis. And then QL, of course, goes straight up. Capacitor QC is negative, so it comes straight down. And so my QL requirement was 1 VAR, but because QC is negative, it reduces the total required power in half. So graphically, I mean, quantitatively, we said, I don't have it here, 1 VAR minus 0.5 VAR, right here, QL and QC. Graphically, if I was to plot the phasor diagram, I'd have QL going straight up, and then QC bringing it down and cutting it in half. And then, of course, when you join total Q together, you get the power triangle. So think on that. Let me know if you have any questions. Again, this is the end of the class today, and then this is the end of the quarter. Yes. Double-sided. It's all there. All of that information is there on the final exam page. It's double-sided. Also, I don't know if I mentioned this in last class, the course evaluations are now open. So go ahead and submit those. Right now, I think your section is at a 29%. It's actually lagging all three. So the morning 9 o'clock session is 56% right there. The section after you is at 53%. So all students in those sections receive 0.5 points of extra credit towards their overall grade. Response rate in this section is about 29%. So there's still time to get it up, bring it up. All right, I'll post it. 0.5 points. 0.5 points. Sure. I'm going to stop the recording here.